Exactly, because it is in this. It is what you are seeing from the screen. Do you understand?
Cross product.
This is MY. Do you guys understand?
Yes.
So let's start. Is it recording already? I cancelled it and is it recording?
I just pressed. This has 42 seconds. Okay.
Timothy, I'm going to run today. So, in this case, we are having axial load and we are having moment. But for a compression member, we are having a load of what? I need energy. A load of what?
A load of 3,000.
Are you sure?
Yes.
No, it's 1,000.
Is that a new question?
Now, major axis, is it x-axis or y-axis?
X-axis.
X-axis. And the major axis moment is what?
Giving 356. 300.
The major axis, remember that when we are dealing with x, it is like this, it is rotating, the moment is like this. Right? The moment is like this. Major axis moment as per x direction. Remember that the axis curve. Right? So x 300, this is mx. Now my. I gave an illustration the other time where we have mx, we have my, and we have mz. In the same fashion of thinking, this is 300, right? Because it's in the x direction. The other one is 75 in the minor axis, and that is my, and that will be like this. Do you understand? Now it's rotating it like this. Do you guys get? You guys are not talking, I'm not.
Yes, I understand.
Do you guys understand?
No.
Picture this and picture what is on the board. This is 300. This is 75. This is 300 because this is x-axis. And mx now on the board is what? 300. That is why it's moving like this. Picture the board, picture this. It is moving like this. The other one, 75, is my. It means it is moving like this. I can't draw it well on the board, but that is just it. That's just what I'm doing. So, let's move to section 98. Sorry, page 98. That's section 4.8.3.1. when we are having a compression member with moments, I hope you are writing. When we are having a compression member with moments, we have two checks according to the code. 4.8.3.1. When we are having compression member with axial load and moments, we'll be having two tests according to the code. 4.8.3.1. Check 1 is cross-section capacity check. Yes. Cross-section capacity check. Open your table to 4.8.3.1. Cross-section capacity check. You can open your table to 4.8.3.1. And the second check is local buckling. Sorry, member buckling or buckling resistance test. Cross-section capacity check. The second one is buckling resistance check. Yes. Or let's call it lateral is. Let's call it flexural buckling test. Or just call it buckling, member buckling. Lateral buckling is for pins. Flexural buckling is for columns. You understand very soon. So I'll start. For the cross-section capacity check, expect this question. For the cross-section capacity check, FC, I remember when we were having steel design tutorial, complete design tutorial for the last session, and I was like, this person will come out. This guy shows himself. And what happened? Came out. Yeah. So expect this person. Based on the code, we have this. Now, who can tell me what this is? What is this? What is this? What is this? What is this? In the... What is this? I love this, I love this. So,
you were just mentioning
now, to get our moment capacity, or in fact, the first stage in any question of steel design is to classify your cross-section. So let's classify. So what do we have for B over T? They gave us a section designation of TD56 by TD68 by 177, of course, universal columns. So what do we have for B over T? B over T. 7 points. What do we have for D over T?
20 B over T is 20.2. 7.8. Okay, it's 8, not 5. Is it 8? Is it 5? It's 7.3.
$20.2, right? Yeah. Now, to classify, where are we going? Which table? Table 11.
Yeah.
What is the condition here? Axial load and what? 11. Axial load and moment. So it means that we're just going to be, for the flange classification, we're going to be using road section. While for the web classification, we're going to be using general. Road section. So what is the limit? 9E. Oh, sorry, what is E? What is E here? 275 over Py. What is Py? First of all, what is our maximum thickness?
23.8 mm.
So it means that Py is 265 from table 9. So now, let's start with class 1. Let's check if it fits in class 1. Now we're classifying the flange. We're classifying the flange. Let's check if it fits in class 1. Class 1 is 9E, right? But what is E? Sorry, what is E? 1.06, Abi? What is E? What is E?
I think approximately
E is 1.02.
Are you sure? Nine E is what? Now, B over T falls in this range, yes or no? Yes. So it means that the flange is what? Classifying the web. No. Since we are doing axial now and bending, for the web, it will be having, I think it was just axial compression, it will be what we did before. If it was just bending, it would be neutral axis. Please write this down. If, for the web now, for classification, if we are just dealing with moments only, it will be pure bending, such that the neutral axis is at mid-depth. This is what we'll be using to classify. Such that neutral axis is at mid-depth. The first case for the web. Check your table 11. Sorry? When we have moments only. But when we are having general, such that we are having stress ratios, it means that we are having axial compression plus bending. But if it is just axial compression alone, the last one for web.
So we are taking the last one for web.
Now we are checking what do we have? Compression and bending. So we are checking. You want to look at class?
Daddy, after you lay down.
I'm coming. I mean, minute, I'm coming. Classifying the web. Classifying the web now. Okay. For web classification, when we have the middle case, which is general, is for when we are having bending and compression. The first case is for when we are having bending and the last case is for when we are having loading.
For the plan, how do you do it? Why is it 9
Exactly. That's what I was thinking about now, because you are thinking that it's supposed to be a compression due to bending, right?
or Asia?
Or Asia compression. Okay, now, Asia compression is for the first one. That we just do, just load. But now, compression due to bending.
I think that compression due to bending is every other thing that is there for the man, which is just like that.
That wait. I'll get back to you guys. But for now, let's just continue. I'll get back to you guys. So, classifying the web. What is R1? What is R1?
FC over DT and P
PYW is PY. FC is 1000.
Yes.
D is what? D
is 20.2. Actually, D not is not this 20.2.
what is T? What is PY? What is R1?
0.9.
Just move on.
They are equal now, they are equal. Check the section classification table. In the flange, this is B, and you have one B, right? So it means they are equal. So SC over AG times PW. AG is what? AG is what? For the section. 40.4. 40.4 or 14?
Is this 0.9?
So what is P? What is AG? What is AG? Do you understand? We're just filling it with dimension. What is AG? PYW. So what is R2? What is R2? What is R2? R2.
It's actually like
Wait, bro. I'm pressing calculator. Lines 265. 0.01 second. 0.017.
So, now that we know R1 and we know R2, we need to plug it inside.
A is the centimeter square. A was giving centimeter square.
226 was the centimeter square. So what is the answer?
So we divide it by
Times, this is in, sorry, this is in, you know it was in kilonewtons, so it's supposed to be converted to newtons. Do you get? Don't worry, this is just a simple step. What's the question? So classifying the web now, we know R1 is 0.9, R2 is equal to 0.017. Perfect, no, just be writing, don't worry. Just be writing, just be writing. So, what is the first limit value? 80E over 1 plus R1. They are correct. I wrote the values here so I can compute. 80E is what? 80 times 1.02 plus 1 plus 0.9. What is the value? It cannot be 17. It cannot be 17. It's between 0 and 1. I mean minus 1 and 1. So what do we have here?
42.95.
What is D over T? Thank God. D over T is 20.2 and it falls inside 42.95. So we're good. This class 1. Go to your code. Go to your code. 11. You should have known that by now. You should have known that it's table 11 by now. D over T. D over T. We are looking at the middle guy. Now, the first check is a class 1 check. And the class 1 check is using 80E over 1 plus R1. Computing this magnitude, we have 42.95. The next question is, does it fall in the limit? Does D over T fall in the limit of 42.95? No. Yes. Simple mathematics. So that is now what? Class what? Class 1. So now, we have that this guy is class 1 and the flange, but are still, because of that question, we are still assuming the flange is class 1, but I'll get back to you guys. But let's use class 1. What happened was that we didn't know whether it was axial due to compression or just road section were to use. So class 1 now. Entire cross-section classification is class 1. Please. Entire cross-sectional classification is class 1. So whatever we are doing, when we are calculating our moment capacity, when we are calculating our buckling resistance, we are going to be using a class 1 section modulus, which is called SX, not ZX. Yes. SX. That's for class 1 when you're entire person. Class 2 is ZX. Class 3 is either is either using a conservative means or using SX. Is ZX effective or SX?
No, ZX or SX.
Class 3 is ZX effective or I don't want to check.
Class 1 is what?
SX, class 2 is ZX, class 3 is you can use ZX effective. Yes, and there's one other thing that is available for you to use. So proceeding, now our moment capacity is next. According to code 4.2.5.2, our moment capacity is depending on whether our share is high or whether our share is low. We can watch the video in Telegram to know whether our share is low or high. But now I'm assuming that the share is low. Share. Sorry?
Yeah, the previous question. Why did you not check?
We didn't use MX, we didn't use moment capacity. So, to know the moment capacity formula to use, you must know whether it is high share or low share. I'm not lying. Go to 4.2.5.2. You see that what I've been saying is in line. So, exactly, I was mixing it up. When it is in class 1 for when it is SX, class 1. When it is XX also, class 2. You can use SX for class 2. When it is ZX, class 3, you can use SX effective. Yes, you can either use ZX for class 3 or SX effective. But there's a limitation to using SX effective. It has the formula in the code. But the limitation of using SX effective is that you're going to be having a very much conservative value. What do I mean by conservative value? It is going to be very expensive because you are going for an extreme safe design. So you are going to use more materials. That is why you are having SX effective. But when you are having Z, okay. When you are having S, okay.
In the question, there's literally no question. Because it was just story. We are not finding any.
I'm going to check whether the section is a good one. So, proceeding. Proceeding with low share and class 1, it means that MC X will be equals to SX times BY, MCY will be equals to SY times BY. That's all. What is SX?
SX is
3460.
343,460. They have converted it to millimeters. This is in centimeters now. Section modulus is in centimeters. What is the unit for section modulus?
Centimeter cube. It's cube.
So what do we have for this?
916.9.
This is not a strange thing, it's just units. Times 10 power 3 to convert 3460 to millimeters. Times 10 power minus 6 to convert it from millimeters to meters, and to convert it from newtons from newtons to kilonewtons. So what do we have? What is MCY? What is MCY? What is SY? What is SY? See, I know that I've lost a lot of us, but I promise you that it's not the right thing.
916.
There was in the orientation that we had where the general sec took us a brief orientation on this. It was like, if you don't get lost in the course, you are not learning it, and that's true. So you're getting lost is a sign that you are pushing. So just be writing. You get
But I'm not lost. I'm not
it's not about that. You are getting it. It's not about now, it's about what you established. Like, for shaking my face. This MCY. Is what? What is the value for MCY? It's part of it. Yeah, just calculate it. What is MCY?
Oh, and next time we will like to do.
What is MCY?
No, 442.5 first.
Have you solved this question before?
But I read it. No, it's 2.55.
So, back to it. What is the... Let's do this now. Now, let's prove this. If we can prove this, it means that it has passed one test. If we can prove this, it means that it has passed one test. Do you get?
Can put it on.